Section 12.5, triple integrals, video 6. So we've talked about the three types of solids, dependent upon whether you view the solid as viewed above and below by two surfaces, from the back and from the front by two surfaces, or from the left and from the right by two surfaces. What if it's all wonky like this? Trust me, we're not going there. I invite you to look it up though. So let's take a look at this example, which is the example number 2 on page 723. Evaluate the triple integral over the solid E of z dv, so a pretty simple integrand, where E is the solid tetrahedron, fancy name for a solid with 4 sides, bounded by the planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. The hardest part about this is sketching E and defining it in terms of the equations that bound it above and below, left and right, and front and back. Quick comment about these planes. The plane x equals 0 is just where x equals 0, so this is the yz plane. The plane where y equals 0 is the xz plane. And the plane z equals 0 is just the yz plane. That's pretty easy to see if you set up a three-dimensional coordinate system. Looks like I'm going to need to get another black marker here in a moment. For example, if x equals 0, you don't move out off the board, so you're stuck on the board in the yz plane. If z equals 0, you don't move up, so you're stuck on the floor in the xy plane. And if y equals 0, you don't move outwards, so you're stuck on the wall on the side in the xz plane. Well, what about the plane x plus y plus z is equal to 1? If you're sketching the plane, sometimes the easiest thing to do is to locate the intercepts. For example, let's find the x-intercept. To be on the x-axis, both y and z have to equal 0. And if I put 0 for y and z, I get x equals 1. So this third plane is going to intersect the x-axis at 1. And in fact, it's going to intersect all the axes at 1. For the y-intercept, you let x and z equal 0, so you get y equals 1. And for the z-intercept, you let x and y equal 0, so you get z equals 1. 3 points uniquely define a plane, so I can just connect them. And remember, it's also bounded by the xy plane down here on the bottom, the xz plane on the left, and the yz plane in the back. So we get this little pyramid shape. It's kind of nestled up in the corner, but that's the solid over which we're integrating. If we're going to set up this triple integral, we have to decide, do we want to look at this as a type 1, type 2, or type 3 solid? In other words, do we want to look at this as something bounded above and below, so above by this plane, on the left and the right, so on the right by this plane, or from front to back, so from the front by this plane? In this case, all 3 of them would actually work. If we did top to bottom, this plane would be the top, the xy plane would be the bottom. If we did left to right, this plane would be on the right, and the xz plane would be on the left. If we did front to back, this plane would be the front, the yz plane would be the back. Let's do it from top to bottom. In other words, we're going to think of this plane as the top surface and the yz plane as the bottom surface. So this top is x plus y plus z is equal to 1, but if we're going to do a type 1, we need to think of that as a function of x and y. In other words, if we're thinking in the z direction, this needs to say z equals. So if we said z equals 1 minus x minus y, that would be what was referred to generically as u2 of xy. You don't have to actually pause and say, hey, u2 of xy is equal to 1 minus x minus y. What's more important is that you solve that equation for z. So on the top of this surface, this plane, z is equal to 1 minus x minus y. That's the top. So what's the bottom? In other words, this space down here. On the bottom, z is equal to 0. So when I set up this integral, I'm going to integrate with respect to z first, and it's going to go from z equals 0 to z equals 1 minus x minus y. But if we're going to integrate this with respect to z first, then we have to look at the projection onto the xy plane. Because when we boil it down to a double integral, we need to look at something in 2 dimensions, not in 3 dimensions. So what does the projection of this tetrahedron look like in the xy plane? Well, if you can picture standing above and looking down, the only thing that you would see would be the shape that's on the xy plane. But I kind of already shaded it in. The projection of this tetrahedron onto the xy plane is precisely this rectangle that's shaded in. So let's export this into 2 dimensions. So x and y. Both intercepts were 1. And so this is our region D. So when we get to the double integral, we'll have to integrate over that. Let's start with setting up the triple integral to begin with. The triple integral over the solid E of z dv is going to be the double integral over that region D of the single integral of z. Now what are we going to integrate with respect to first? This is going to be our upper limit for the first integral. This is going to be our lower limit. So our lower limit is going to be z. Our upper limit is going to be 1 minus x minus y. Am I integrating dz, dx, or dy? Answer, dz, for 2 reasons. I can't integrate with respect to x or y if either one is in the limit of integration. Secondly, we're thinking top to bottom, that's in the z direction. So this is a dz integral. And then we'll worry about the double integral after we get past the dz integral. Well, the dz integral is pretty straightforward. The integral of z is 1/2 z squared. And we're going to evaluate it from z equals this to z equals that. Let's go ahead and just work that out over here. I'm just looking for room to write things. Integral from 0 to 1 minus x minus y of z dz is 1/2 z squared from z equals, well, I'm just going to write 0 because z is the only variable here, to 1 minus x minus y. So if I substitute 1 minus x minus y for z squared, I get 1/2 1 minus x minus y squared. Minus, if I substitute 0, I get 0. So this is the value of the first integral. So now we're down to the double integral over the region D, the projection of the solid onto the xy plane of that thing, 1/2 1 minus x minus y squared dA. And now we have to shift gears and think about how to integrate this over this region. Now, we could integrate with respect to x or with respect to y. It all depends upon if you want to look at this region as being defined on the top by this line, on the bottom by that one, or on the right by that line and on the left by this one. Let's go top to bottom. To me, top to bottom is always the best approach to take. On the bottom of this region, y is equal to 0. But what is y equal on this, this line? Well, do you know the equation of that line? Think about it. This line is this plane in the xy plane. In other words, this line on the top is the intersection of this plane with the xy plane. And what do we know about every point on the xy plane? Z is equal to 0. So if I put z equal to 0 into the equation of this plane, I get x plus y equals 1. Now, you could also do it old school. In other words, this point in the xy plane is 1, 0. This point is 0, 1. You could calculate the slope to get -1. And there's the y-intercept. So you could say y equals -1x plus 1, which is exactly the same thing I would get if z is equal to 0 and I move the x over. So no matter how you approach it, the equation of the line on the top of this is y equals -x plus 1. So we can integrate over this region with respect to y, because in the y direction, the bottom is 0 and the top is negative x plus 1. So let's set up a double integral of 1/2 quantity 1 minus x minus y squared. We're going to do dy first. The y's from bottom to top are 0 to negative x plus 1. And that would leave dx last. When you get to the last integral, it's just an interval of constants, an interval of values. These x's are being integrated over the range 0 to 1, so not a whole lot to look at there. Again, the setup is everything. The actual evaluation of the integral is a calculus 1 problem. It's the setup. Now we're not done, and I'm going to have to erase something, so we're going to pick it up from here. And unfortunately, I got to get rid of this beautiful picture. Again, this problem is in the book. It is on page 723. The author pretty much says everything that I'm saying. That's good, because I'm right, and he should be right also. Otherwise, he shouldn't be publishing books. All right, so let's focus on this now, iterated integral, by looking at the inner integral first. So let's take this out, and then once we get its answer, we'll import it back into the remaining integral. So the integral from 0 to negative x plus 1 of 1/2 parentheses 1 minus x minus y close parentheses squared dy. How do you do this one? You could do a substitution. You could say u equals all this stuff. And remember, if we're integrating with respect to y, the x is a constant. So if I said u equals this, its derivative would be negative 1. So to balance out the substitution, I would need an extra negative. Well, let me write this down. If we did the substitution, u equals, and I really shouldn't use u because I used it earlier, but it's erased, so we're okay. If I said u equals this, then du would equal negative dy. Derivative is 0, derivative is negative 1. So to make the du substitution, I would need an extra negative on the dy, which means I would need an extra negative to balance it out. So it would be the integral of negative 1/2 u squared du from y equals 0 to y equals negative x plus 1. Why did I just write y equals? Because I just changed the variable, but I didn't change the limits of integration. So this integral would be negative 1/6 u to the third. Let me take the derivative real quick to make sure it's good. It is. This is being evaluated from y equals 0 to y equals negative x plus 1. So I need to bring back the substitution. Negative 1/6 quantity 1 minus x minus y close parentheses cubed, almost botched that up, integrated from y equals 0 to y equals negative x plus 1. And I'm still writing y equals because I have multiple variables over here. So we need to substitute negative x plus 1 for the y and 0 for the y and subtract the results. If we substitute negative x plus 1 for the y, then this parentheses becomes 1 minus x minus. If this negative gets distributed to both of these, I get a positive x and a negative 1. So it's actually positive x and negative 1 to the third power minus negative 1/6 parentheses, substitute a 0 for the y, I get 1 minus x to the third power. And now we need to clean this mess up. Luckily, inside the first parentheses, the x's cancel. Wait a minute, not only do the x's cancel, the 1's cancel. This is 0. The whole front chunk disappears. Goodbye. Not the same over here, but it's not that bad. Only issue is I got a double negative, so it becomes a positive. 1/6, 1 minus x to the third power. 2 integrals down, 1 to go. And again, the integration is straightforward. In theory, you already know how to pull off all these integrals. Just be careful and be persistent. But now that we've evaluated the second integral, let's import its result back into the remaining integral. So, resuming, we have the integral from 0 to 1 of the answer to what we just got. So 1/6 times 1 minus x to the third power dx. We could do a substitution again, but just like before, the du would equal negative dx. So the only thing I have to do to balance it out is throw in an extra negative. So I'll just throw in an extra negative and integrate it. The integral of 1 minus x to the third is 1/4 1 minus x to the fourth, and this is being evaluated from 0 to 1. I'm going to take the derivative just to make sure I didn't botch anything up. If I took the derivative, the 4 would come down and cancel the 1/4. This would become a 3. Chain rule, derivative of the inside is -1. That would hit that negative, turn it back into a positive. Everything's good. I should probably call this -1/24. I'll do that in the next step. -1/24 times, substitute 1 minus 1 to the fourth, that's convenient, minus -1/24, substitute 0, 1 minus 0 to the fourth. So we get -1/24, 0 to the fourth, plus 1/24, 1 to the fourth. First part disappears, second part is just 1/24. Piece of cake. And I could have done this integral 3 different ways, actually 6 different ways, depending upon if I wanted to think of the original solid as top to bottom surfaces, front to back surfaces, or left to right surfaces. And when I got down to the region, I know I did top to bottom, and so it was dx and then dy and then dx, but I could have also done it left to right and then done dx and then dy last. But all of the different approaches to this one would give you the same answer, 1/24. You might want to rewatch this video. Ooh, that was a long video.